Hello everyone, welcome to this lecture. The plan for this lecture is as follows. So, in this lecture we will see a very nice cryptographic application based on the concepts related to finite fields, namely secret sharing. So, earlier my plan was to cover both additive secret sharing as well as Shamir secret sharing. We will see, depending upon the availability of time, whether we are going to cover both of these topics or not. So, let us start with the problem of secret sharing, what exactly its motivation, real world application. So, for that, imagine a banking application and the way a locker is operated, right. So, I do not know whether you have a locker account in a bank or not, but I do have, and the way a locker account is maintained or operated in the bank is as follows. Whenever you want to open or get access to your locker, you have to go along with your key, and apart from your key there is another key which is held by the manager, and only when both I enter my key as well as the manager enters the key, the locker can be opened. That means in my absence the manager cannot open the locker, and in the same way I alone cannot go and open the locker myself just using my copy of the key. So, now in the same way, here in this particular example I consider a scenario where you can imagine that a locker can be opened by pressing the keyword or the key phrase, whatever you can call, and the key phrase is not available with a single person. So, I imagine here that we have 3 managers, manager 1, manager 2 and manager 3, and the way this system works here is the following. Only when at least 2 of the managers come together and enter their respective passwords, the locker can be opened, but if only a single manager goes and tries to open the locker by entering his or her password, the locker should not be opened, right. So, for instance, if M1 just simply goes and try to enter, the locker should not open. Similarly, if M2 goes and try to open the locker alone, he should fail. If the manager M3 alone tries to open the locker, she should fail, and so on. But say if the first and the second manager goes together and enter their respective passwords, then the locker should be opened. In the same way, if the first and the third manager goes together and enter their respective passwords, the locker should be opened. Another interesting motivation for secret sharing problem is the following. So, it is believed that in the 90s the access to Russia's nuclear weapon was done in the following fashion. So, the password or the credential for launching the nuclear weapon was shared among 3 top entities of the country, namely the president, prime minister and the defense minister, and it was shared in such a way that the nuclear weapon could be launched or could be accessed only if at least 2 of the above 3 entities come together and enter their respective credentials or passwords. But if only one entity comes and try to launch the nuclear weapon, then that entity should fail. Okay. So, in some sense you can imagine that this kind of system gives you more security, more robustness, in the sense that if one of the 3 entities, say either the president or the prime minister or the defense minister, gets compromised and leaks the password, then an enemy country can launch the nuclear weapon. But if we operate our nuclear weapon in this kind of system, then in order that the system gets compromised, the enemy country has to compromise at least 2 entities. That means, if it just compromise one of the entities, say either the president or the prime minister or the defense minister, then still no harm will be caused. Only when 2 of the entities are compromised, the harm can be caused in the system. In that sense, the system is more secure. Okay. So, now let us abstract both the examples that we had seen by this general problem of what we call as n comma t secret sharing, and this problem or this primitive was independently introduced by Turing Award winner Shamir in 1979, and by Blackley in the same year. Okay. So, I am taking this slide from Juan Garay. So, the problem definition is the following: you have a set of parties P1 to Pn. So, n is a given parameter, everyone knows the identity of the parties. We call these parties as shareholders. Okay. And among these n parties, there is a designated entity or a special entity whom we call as a dealer, denoted by D. And dealer has some private input, some secret input, let us denote it by S, which is a bit string, okay, or it could be any abstract value, but you can always assume that it is a bit string, and this value S belongs to a bigger set, namely this set fancy set, which I call as the secret space. Okay. So, the knowledge of the secret space is publicly known, namely it denotes a set of all possible secrets which dealer can have. What exactly is the value of the secret from the secret space which dealer has, no one will be knowing, depending upon what kind of prior information we may have about that about that secret is, but it will be a public knowledge that whatever is the input of the dealer, it is from a bigger space, namely this set fancy S, which we call as a secret space. So, for instance, a simple example of the secret space could be the set of all possible bit strings of length say L bits. That is the case, then everyone will be knowing that okay, dealer is going to invoke or use this primitive with some value S belonging to the set of all possible L bit strings. Okay. And everyone will know the identity of the dealer. Now, the goal is the following: we want a mechanism according to which dealer should share this secret S among the shareholders. By that I mean we need a mechanism according to which dealer should compute n pieces of information, denote them as S1 to Sn, and the ith piece of information, namely Si, will be given to the ith party, right. So, we say that Si denotes the share of the secret S for the party Pi. That is a requirement, but then if that is just my requirement, it is very easy to solve this problem, right. Dealer can say if dealer can do some kind of distribution, give some piece of information regarding S to the first shareholder, some piece of information regarding the secret to the shareholder and second shareholder, and so on. So, that is why to make the problem interesting and to model what exactly we had seen in the previous two examples, we need the following requirements from this sharing mechanism. We require that it should be impossible for any set of t or less number of shareholders to pool their shares and reconstruct back the secret S. Okay. So, again like n, t is also some given parameter. So, I need my sharing mechanism to be such that the vector of n shares, which I denote as S1 to Sn, they should be such that if any t pieces of these, if any t shares from this vector are taken, then it should be impossible to reconstruct back the secret S, irrespective of how much time I give to you, how much resource I give it to you. Okay. And this should hold even if the description of the sharing algorithm, the description of the secret space, everything is publicly known. That is important. I am not assuming here that the sharing mechanism, the algorithm by which the shares are computed, they are hidden, it is known only to dealer. No, that is not the case, because dealer could be any party, the n shareholders could be any party. I cannot afford to design an algorithm which is known or which is secret and available only with the dealer, right. So, So, that is my first requirement. The second requirement is that if t plus 1 or more shares are available from this vector of n shares, then it should be possible to efficiently and uniquely reconstruct back the secret. So, you can imagine here that t is kind of acting as a threshold here. Any number of shares up to t or less will fail to give you back the secret. Any number of shares which are t plus 1 or more in numbers should give you back the secret unambiguously, right. So, for instance, the previous two examples that we had seen there my threshold t was 1. So, for example, and my n was 3. So, if you take the banking example, there were 3 managers, right. So, there we want a mechanism where the master password should be shared among 3 managers, namely 3 shareholders, so that if any one of the 3 managers try to access the secret, the manager should fail. In the same way, in the nuclear weapon example, we had 3 entities, namely the president, the vice president and the prime minister. So, they are my shareholders and my t was 1. I do not want any one of those 3 entities to be able to access the nuclear weapon, but only when 2 or more number of entities come together, they should be able to access the nuclear weapon. So, that was my requirement. So, this is your problem of n comma t secret sharing. Okay. Now, the question is how exactly we can solve this. So, let me discuss this n comma t secret sharing scheme due to Shamir. So, this is also called as Shamir's n comma t secret sharing scheme. He gave a very nice and very elegant solution for solving the n comma t secret sharing problem. Independently, Blackley gave another solution for solving the n comma t secret sharing problem, but since we want to see the solution based on applications of or concepts learned for finite field, I am going to demonstrate Shamir's secret sharing scheme for you. Okay. So, this algorithm was published way back in 79 in this very short paper, but this is one of the highly cited research papers in cryptography. Okay. And this is a very simple and elegant construction. In fact, this is my personal favorite. When I will explain you the solution, you can't even imagine that how can the solution be so simple and at the same time elegant. So, the idea behind Shamir's secret sharing scheme is the following. So, imagine dealer has this secret S. Okay. So, to share the secret S, what dealer can do is the following. It can pick a polynomial of degree t, say in variable x, and it will be a random polynomial which will be chosen by the dealer. When I say a random polynomial, by that I mean only dealer will be knowing the coefficients of the polynomial f of x. So, say for instance, if f of x is of the form say a naught plus a 1 times x and like that, the t plus 1th coefficient is a t and x raised to power t. So, when I say randomly choosing the polynomial, by that I mean that the coefficients a naught to a t are known only to the dealer and it is not known to any shareholder. This does not violate the assumption that the algorithm description is publicly known. The algorithm is publicly known. What is the algorithm? The algorithm here is choosing a polynomial randomly. That is the process, that is the step. That step is publicly known. That means the shareholders will be knowing the actions of the dealer. Actions of the dealer, by that I mean they will be knowing that okay, dealer is going to pick a polynomial f of x, but what exactly is the polynomial, the value of the polynomial, that will not be known to the shareholders. That will be random, that will be known only to the dealer, because if everything is known in the public domain regarding what are the values which are picked by the dealer and so on, then how at the first place you can hope to solve this problem. There has to be some component of randomness in this whole solution, and that is incorporated by saying that dealer picks the polynomial f of x randomly. Now, it is a random polynomial except that the constant term of this polynomial is the secret which dealer wants to share. That means, the coefficients a1, a2 and a of t, they are randomly chosen, but a naught is not randomly chosen, but rather a naught is actually the secret s which dealer wants to share. In some sense, you can also imagine this as if the polynomial f of x is a random polynomial, except that the polynomial when evaluated at x equal to 0 will give you the value s. Because if I pick a polynomial of the form f of x where the constant term or the coefficient is the secret s, and then you have the remaining coefficients, then that polynomial when I evaluate at x equal to 0 will give me the value s. Okay. And then once dealer has chosen this polynomial f of x randomly, the shares are nothing but distinct points on the polynomial chosen by the dealer. Okay. So, let me demonstrate what I am trying to say here, and for demonstration I assume that I need a secret sharing mechanism where t is equal to 1, and imagine dealer's secret is s. So, a polynomial of degree t equal to 1 is nothing but a straight line. So, what I am saying here is that dealer in his mind is picking a random straight line, and that straight line has the property that when evaluated at 0 will give you, when evaluated at x equal to 0 will give you the value s, namely his secret. And now the shares for the respective shareholders are the following. We imagine here that alpha 1, alpha 2, alpha 3. Okay. So, by the way I am assuming here n equal to 3. So, we need to compute 3 shares, and for computing 3 shares for the 3 shareholders, we assume here that alpha 1, alpha 2 and alpha 3 they are some publicly known distinct non-zero values, and the share for the first shareholder is nothing but the value of this straight line at x equal to alpha 1. Namely, we compute the point alpha 1 comma s 1, we compute the point alpha 2 comma s 2, and we compute the point alpha 3 comma s 3, which are equivalent to saying, which is equivalent to saying that I am evaluating this straight line at x equal to alpha 1, x equal to alpha 2 and x equal to alpha 3, and getting the values s 1, s 2 and s 3, and s 1 will be the share given to the first shareholder, s 2 will be the share given to the second shareholder, and s 3 will be the share given to the third shareholder. Again here everyone will know the value of alpha 1, alpha 2, alpha 3, that is not hidden, and everyone will know that the first shareholder is getting the value of dealer's straight line at x equal to alpha 1, but what exactly was the straight line, that is not known, that is important. Similarly, everyone will know that the second shareholder is getting the value of dealer's straight line at x equal to alpha 2, and everyone will know that the third shareholder is getting the value of dealer's straight line at x equal to alpha 3, because the steps of the algorithm are publicly known. Now, let us see here why this constitutes a valid n comma t secret sharing scheme. So, remember I am considering the case where n is equal to 3 and t is equal to 1. The reason it constitutes an n comma t secret sharing scheme is because of the following two facts. Since the dealer's polynomial f of x, which was known only to the dealer, is unknown and its degree is t, it follows from fundamental properties of polynomials that if I give you t plus 1 or more number of distinct values of the polynomial, then you will be able to uniquely reconstruct back your polynomial. So, for instance, since t is equal to 1 here and the straight line which was chosen by the dealer is not known to you, what I am saying is the following: if I give you two distinct points on the straight line which dealer has chosen, then you will be able to uniquely get back the straight line which was chosen by the dealer. And if you can get back the straight line which was chosen by the dealer, well, you will be knowing the secret which dealer has shared, because the constant term of that straight line, right, is nothing but the dealer's secret, right. So, for instance, if I give you the first two shares, then the first two shares are nothing but alpha 1 comma s1 and alpha 2 comma s2. Now, using these 2 points, you will be able to get back this straight line uniquely, and once you get back this straight line, you can get back the secret s. In the same way, if I give you say the second share and the third share, you will be able to get back the dealer's straight line uniquely, right, and hence dealer's secret. So, that is the first observation. So, that shows that t plus 1 or more number of shares will indeed give you back dealer's secret uniquely. That satisfies one of the properties of n comma t secret sharing. Now, the second observation here is that if instead of t plus 1 shares I give you only t shares, and t shares here are nothing but in this context they constitute t distinct values of an unknown polynomial whose degree was t. So, the second observation here is that if I give you t unknown values, if I give you t distinct values on an unknown t degree polynomial, then you cannot uniquely recover back the polynomial f of x. So, what does that mean here in the context of this example where t is equal to 1? It means the following: suppose the first shareholder who has the share S1 and of course, it knows alpha 1. The question here is it possible for the first shareholder to get back the dealer's secret? Well, no, because it is possible that through the point alpha 1 comma S1, this blue straight line is actually the line which dealer has selected. That means, it could be possible that dealer has actually selected this blue straight line for sharing, and this blue straight line when evaluated at alpha 1 gives you the value S1, namely the point alpha 1 comma S1 lies on this straight line. That could be the case. If that could be the case, then the secret would have been S double prime, where S double prime would be the constant term of this polynomial, or it could be equally likely the case that dealer has actually used this straight line which also passed through alpha 1 comma S1, or it could be the case that dealer has used say another straight line which also passes through alpha 1 comma S1 and so on. So, that means just using the first share S1, it is simply not possible to exactly identify the straight line which dealer has used, and hence it could be any straight line, and hence it could be any secret which dealer would have shared, right. So, that means you do not have sufficient information if you are just given t shares to uniquely reconstruct back the dealer's unknown polynomial, and hence you cannot uniquely get back dealer's secret. That is the intuitive idea, right, a very basic fundamental fact of polynomials of t degree, namely t plus 1 or more points are sufficient to get back the polynomial, t or less number of points are inefficient are not sufficient to uniquely get back the polynomial. Now, in the Shamir secret sharing scheme, we perform or we use the above idea where all the computations are performed over a finite field, namely my secret space will be a finite field, my polynomials will be selected over a finite field, and my shares also will be elements of a finite field. And this is done because of the following two reasons. We need to maintain security. Intuitively, what do I mean here is that if instead of picking the polynomial over a field, we pick polynomial over integers, namely if my coefficients of the polynomial are integers, then based on the magnitude of the shares, I may end up revealing some information about the range of the possible range of the secret. I may not be able to give the exact leak the exact value of the secret, but I may be leaking some information regarding the possible range of the secret. And also if I pick my coefficients of the polynomial and the shares from the integers, then actually I will be working over an infinite domain, which I would not like to do. So, that is why everything is embedded to a finite field. Okay. So, to understand the actual Shamir secret sharing protocol, let us again recap the concepts regarding polynomials over a finite field. So, if you are given an abstract field which is finite with an abstract plus and dot operation, then a polynomial over the field is exactly a polynomial over the integers, where the difference is that now all the coefficients are from the field and all the plus and dot operations are your field operations. A value x from the field will be called a root of this polynomial f of x if the polynomial f when evaluated at x gives you the additive identity 0 or the 0 element of the field. Then we can show that we have actually shown in our discussion on abstract algebra that you take any polynomial of degree t, then it can have at most t roots. And using this theorem, we can actually show that you take two different polynomials f of x and g of x over the field, then they can agree on at most t points. That means, you can have at most t common points lying on both f of x as well as g of x, right. It is like saying the following: you take two straight lines, there can be at most one point which is lying both on the first straight line as well as on the second straight line. You can't have 2 points, right, which are common and lying on both the first straight line as well as on the second straight line, because if that is the case, that means the two straight lines are the same straight line at the first place. So, that is why we can extend that idea in the context of polynomials over field as well, and then conclude that if you take two distinct t degree polynomials, they can agree on at most t points. Now, another interesting result from the abstract algebra is the following: if I give you t plus 1 number of x y values, where the x components are the distinct, then you can always find a unique t degree polynomial over the field such that this x comma y values constitute distinct points on that f polynomial. Okay. So, this is often called as Lagrange's interpolation theorem. So, basically the process by which we can compute this f polynomial is called as the Lagrange's interpolation. And here is how we can get back this unique polynomial f of x. I define several t degree polynomials. So, the ith t degree polynomial in x is called as the delta ix polynomial, and it will be of this form, right. So, why it will be of degree t? Because in the numerator you have t factors of the form x minus some value, and in the denominator you have the product of several differences. Okay. So, since this whole polynomial is over a field, do not interpret this division your numerical division and integer division. The interpretation of this division is the following. In the denominator I have the terms xi minus x1, xi minus x2, xi minus xi minus 1 and so on. All these are elements from the field, and if I take the differences here, they will be elements of the field. So, in the denominator I have the product of several field elements. So, let the final result of the product of the elements in the denominator is A. Then the interpretation of this delta ix polynomial is that instead of saying I divide the numerator by A, I should interpret it as if the numerator is multiplied with A inverse, where A inverse the multiplicative inverse of the element A, because I am performing all the operations over the field. So, in field I have just a plus operation and the dot operation. So, division should be interpreted as if I am multiplying with the multiplicative inverse. Okay. So, the property of this delta ix polynomial is the following. If I substitute x equal to small xi, then I get the value 1, because if I substitute x equal to xi, then both the numerator and the denominator become same. Whereas, if I substitute x to be any other value of x, little x, say little x1, little x2 and so on, then I get the value 0, because my numerator, one of the terms in the one of the factors in the numerator will become 0, and 0 multiplied with any element will give me 0. Okay. So, now the unknown f of x polynomial, which I can recover from this t plus 1 distinct x y pairs, is the following. It is the product of these t plus 1 delta x polynomials multiplied with the corresponding y values. So, the first delta polynomial multiplied with y 1, second delta polynomial multiplied with y 2, and the t plus 1th delta polynomial multiplied with the t plus 1th y value. And you can check easily here that you take this polynomial f of x and evaluate it at xi, you will get the value yi, because when you evaluate this f of x polynomial at xi, then only the delta I x polynomial will survive and give 1, and that will be multiplied with yi. So, you will get yi, and all other remaining delta I x polynomial will vanish. Okay. That is the idea of this Lagrange interpolation. So, now based on this concept from the finite field, here is the actual Shamir secret sharing scheme. So, the setup here will be the description of a finite field. We require the size of the field to be at least n, namely the number of shareholders, and there will be n distinct values, x values from the field which are non-zero and which will be publicly available. To share a secret S, which is an element from the field, which ensures that my secret space fancy S here is actually the finite field. So, if there are multiple elements from the field which dealer wants to share, he has to invoke this protocol multiple times, but imagine he has only one element from the field which it wants to share, then to do that dealer is going to do the following. It is going to pick t coefficients for the sharing polynomial randomly from the field. So, this notation belongs to subscript r, denotes that the polynomial is randomly chosen. So, the polynomial f of x is randomly chosen, except that its constant term is the secret which dealer wants to share. And now, the share for the ith party is the evaluation of this polynomial at x equal to xi. Of course, all operations done over a finite field. Now, let us see whether this scheme satisfies the two requirements of secret sharing. The first requirement is that if you take any t plus 1 shares, you should be able to get back the original secret, and this comes from our Lagrange interpolation, because t plus 1 shares are nothing but t plus 1 distinct evaluations of the unknown t degree polynomial. Why they are distinct evaluations? Because we have chosen our x values, namely the values at which the polynomial is evaluated, to be distinct. Whereas, for privacy, namely we have to show that you take any t shares it leaks no information about the underlying secret S, even if the T shareholders who combine their shares, they are computationally unbounded, they have infinite resources and time. And intuitively this follows from the fact that if I take the vector of n shares which I computed by the dealer, the property of these n shares is that you take any subset of T shares from this vector, its probability distribution is independent of the actual secret S. Okay. That means, say for instance, if I take the first T shares here S1 to St, then what I am saying is it does not matter whether your secret that was shared was S or the secret that was shared was S prime, with equal probability the first T shares could be S1 to St even for the secret S, and with equal probability the same set of shares S1 to St could be the shares for the secret S prime as well. So, let us prove this formally. So, for that let me define this set F raised superscript St, which denotes a set of all possible T degree polynomials over the field whose constant term is the secret S. And how many such polynomials I can have? Well, I can have order of the field raised to power T such polynomials. This is because any polynomial in this set will be of this form, where the constant term is fixed, but you have the flexibility to choose the remaining T coefficients, and for each of the remaining T coefficients of this polynomial, of any polynomial in this set, you have order of field number of options, because they could be any element from the field. So, that is why you can have these many number of possible polynomials over the field whose constant term is the secret S. Okay. Now, my goal is to show that the probability distribution of any T shares computed in an instance of Shamir secret sharing is independent of the actual share of the actual secret. So, for proving that, I imagine here that let the first T shareholders are the corrupt shareholders. That means, I want to prove that the probability distribution of the first T shares are independent of the actual secret which is shared. You can prove that the probability distribution on any subset of T shares is independent of the actual secret, but for simplicity I am proving with respect to the first T shares here. So, my claim here is the following: if I give you arbitrary value of the first T shares, there exists a unique polynomial of degree T with constant term being the secret S, such that this S1 to St could occur as the shares could occur as the first T shares. And this is because in order that S1 to St constitutes the shares or the first T shares for the secret S, it should be the case that there should be a T degree polynomial whose value at 0 should be S, whose value at alpha 1 should be S1, whose value at alpha 2 should be S2, and like that whose value at alpha t could be St. And there could be only one such polynomial. You can't have two different polynomials, say f1 of x as well as f2 of x, simultaneously passing through all these points, because you have t plus 1 of these points in number, and we have proved that two different T degree polynomials can have common values at most t points, right. That means, at most t points could be common both to f1 of x as well as f2 of x. You can't have t plus 1 points common to both f1 of x as well as f2 of x. That is a simple fact here. Now, to prove that the probability distribution of the first T shares is independent of the actual secret, let us take two possible candidate secrets which could be shared in an instance of Shamir secret sharing scheme, call them as S and S prime. My claim is that it does not matter whether the secret is S or whether the secret is S prime, with equal probability you could get S1 to St as the first T shares in an instance of Shamir secret sharing scheme. Basically, I want to calculate the following two conditional probabilities. The first conditional probability here is that given that the secret shared is S in an instance of Shamir secret sharing scheme, what is the probability that the first T shares are S1 to ST? And the second conditional probability here is that given that the secret shared is S prime, where of course S prime is different from S, what is the probability that the same values S1 to ST occurs as the first T shares in that instance of Shamir secret sharing scheme? And it is easy to see that both these conditional probabilities are exactly the same, namely 1 over field raised to the power t, because in order that the shares S1 to ST occurs in an instance of Shamir secret sharing where the shared secret is S, it should be the case that dealer should have chosen the unique t degree polynomial f of x during the sharing phase for sharing S, which passes through the points 0 comma s, alpha 1 comma s1 and like that alpha t comma st. But what is the probability that among all possible polynomials from this set f superscript st, dealer actually chose this polynomial f of x? Well, it is 1 over f power t, field size power t. In the same way, what is the probability that if dealer wanted to share the secret S prime, it would result the first T shares to be S1 to ST? The probability of that is exactly the same as the probability that dealer chooses that unique polynomial of degree t, say g of x, from this collection f superscript S prime t passing through the points 0 comma S prime, alpha 1 comma S1 and like that alpha t comma st. But there are field size raised to power t number of polynomials which dealer could have used for secret sharing S prime. Among those f field size raised to power t polynomials, the probability that dealer has actually chosen the polynomial g of x is again 1 over field size raised to power t. So, that shows it does not matter whether the secret shared is S or S prime, with equal probability the shares S1 to ST could occur as the first T shares. That means, the probability distribution of those T shares is independent of the actual secret, and which formally proves that your Shamir secret sharing scheme does not reveal any information if T shares are compromised. So, with that I conclude today's lecture. I have not given full formal proofs, I have given you intuitive arguments for the privacy proof here. If you want to see the references for today's lecture, then you can refer to my NPTEL course titled Foundations of Cryptography, and this is the link for this course. Thank you.